Thank you very much. I'm very happy to be here and celebrate these three people, all three of which I really, really like. Pat was my co-supervisor in Calgary when I did my PhD, and I learned a lot from him. And then I moved back to Hungary, and I learned really, really a lot from both Gabor and Andres. So I'm really grateful to all three of you, and I hope you will enjoy this talk. So I'm going to talk about covering space or covering a convex body by a given convex body, translates of a given convex body first. So let me start with this classical result of Rogers. So we're given a convex body, a fixed convex body, and we want to cover the whole space with translates of this body. And Rogers proved that you can do it with rather low density. So I hope it's okay if I don't define density. So for those who don't know what density is what you think density should be. So take a box and count the total volume in the box divided by the volume of the box, and then you let the size of the box go to infinity. So this is a rather low bound, especially compared to the lower bound that if you take the Euclidean ball and you want to cover space with translates of the Euclidean ball, then the density will not drop below some constant times d. So even for the ball, the truth is somewhere between constant times d and d log d. So it's an old result and pretty sharp. Now, when you want to cover a particular convex body, so K, you want to cover K by translates of L. Then an obvious lower bound, so this is the covering number, n. So the number of translates of L needed to cover K, the minimum number of translates. Obviously, the ratio of the volumes is a lower bound, and a very simple averaging argument from this bound above gives this upper bound. So the idea is you take translates of L that cover K, that cover the whole space with this relatively low density, and then you just want to find a good translate of K that doesn't intersect too many of these copies of L, and an averaging argument yields this. And there are similar results in the sphere, on the sphere using caps, covering the sphere with caps, and so all these results somehow follow the similar pattern. So Rogers' idea. So his idea is the following: that first you cover most of space or most of the region that you want to cover randomly. So you just pick translates randomly, sufficiently many so that much of space is covered, but you don't pick too many. And then, well, there is a gap. There is some uncovered region, and then you just cover the gap greedily. So there you kind of covering the gap is an expensive thing. Covering most of space is very cheap, and then on average you end up with rather cheap, very low cost. Now, another method is the following, and I couldn't trace it back further, but I would imagine that this is not really the first paper where it appeared. It's Odette Schramm's paper on illumination of sets of constant width, where the idea is the following: you want to cover a set, and instead of covering this set, let's say you want to cover a box, and instead of covering the box, you take a delta net lambda in this box. So delta net meaning like a metric delta net. Okay, so it's a dense enough set, lambda, and cover this lambda. So let's say you had a box, and then this lambda is a finite set. So instead of covering the box, you want to cover this finite set. Well, not by translates of L, but by translates of slightly shrunk copies of L. And so you cover this dense enough subset, this finite set, lambda, by translates of this slightly shrunk copy of L. And then if you cover lambda, then once you grow L back. So once you replace these shrunk copies with the original copies of L, you actually get the covering of the whole box. So that's another idea, and then a little bit of a modification, and how to cover this delta net? Well, randomly again. So you take random translates of L or random copies of L that will cover your delta net. And the modification of this is to use a simple lemma, which I'm gonna state. Well, a simple sounding lemma, which is due to Lovász and independently to Stein, to cover this lambda, and then we do this. So this shrinking and enlargement, just like previously. So the difference between these two methods is that this lemma of Lovász and Stein is non-probabilistic. So you have a finite set. You want to cover it economically. Then you can do it in an algorithmic way. And also using this approach, you get really short, really simple proofs. So let me give a general result along these lines. So using this method. So here I just have the definition of the covering number. So I want to cover K by translates of L. That's N. And let me define fractional covering. So what's a fractional covering? So what is a covering? So I want to cover K by translates of L. What does it mean? Well, it means that for any point of K, so for any point of K, if I take x minus L, then there has to be a translation vector in x minus L, right? Because that's exactly what it means. If I select translation vectors, x is covered by a translate of L if there is a translation vector in x minus L. Now, in the fractional setting, instead of picking a translation vector in each set x minus L, we want a measure. We want the measure of these x minus L's to be large enough. So instead of picking some points, we're looking for a measure on the whole space such that each of these sets have measure at least one, and that is it's correct. It's right to call it a fractional covering, and so the fractional covering number, this n star, is the smallest total measure of space when you have a fractional covering, and so a result that goes back to Einstein, Avidan, and Slomka, and then I gave a different proof later on, says the following, that, well, we want some connection between n and n star. Now, obviously, it's easy to see that if you have a covering, let's say 10 copies of K cover L, 10 copies of L cover K, then n star is also at most 10. So if you have an integral covering, a real covering, then you obviously get a fractional covering. So this bound is just comes from the definition. If you think about it, this is the solution of a linear programming. This is the solution of an integer programming problem, and n star is the solution of the linear relaxation of this problem. But the interesting part is to go from above. So can we bound n from above in terms of n star? And so here's this bound that the covering number can be bounded by n star with this error. And so what's this error? So we have our delta net lambda, and it's the size of this delta net intersected with translates of our slightly shrunk copy of this is I'm writing roughly because I don't want to be quantitatively precise here, so here is the key to this result. So the key is the following. It's a purely combinatorial result. So forget geometry. There is no sets, no RD, no nothing. There is just a finite set lambda and a family of subsets of this set, and we want to cover our set with this family. So you can call it a hypergraph or set family or whatever terminology you like. And so the covering number, the minimum number of sets from our set family that will cover lambda is bounded here by this expression where, well, tau star is the fractional covering. So the covering number is, the fractional covering number is defined in the obvious way. And so this multiplied, so the fractional covering number multiplied is essentially by the logarithm of the maximum size of a set in your family. And the nice thing about this lemma is that not only does it give this quantitative bound, but also it says that the greedy algorithm yields this bound. So it's algorithmic, it's not probabilistic. And then essentially to prove to prove this result, essentially all you need to do is substitute in this lemma, and you get it. So in a way, the difficulty is hidden in the proof of this lemma, which is of course a very neat proof. So what this method is good for, first of all, it gives a different proof for Rogers' result and for Rogers' covering density result, and it's a very simple proof. It's like a few lines long proof, and also you can obtain new covering results both on the sphere and in space, and this same method was recently used by Prosanov to reprove the result of Larman and Rogers on the chromatic number of Euclidean space. So the idea here, the philosophy is you have a covering problem and separate the geometric part and the combinatorial part. And what's nice here, let me just go back to this theorem here, is that we separate it in a formula. So the combinatorial part is this Lovász-Stein lemma itself, and the geometric question is this. So then your geometric question is to give a good fractional covering, or give a good measure. Often this measure is just volume, but sometimes you can do better. You can be smarter than just using volume. So that's computing or bounding n star is what I call a geometric problem, and then using the Lovász-Stein lemma is just a combinatorial idea. So one natural way of going forward is to ask about multiple coverings. So when you don't want to cover your set, so you're given a set. Now I'm in the abstract setting, in the combinatorial setting. So given a finite set and some family of subsets of this set, and you don't just want to select a small subfamily of this family which covers your set, but you want to select a subfamily which covers every point f times. So now we're talking about f-fold covering. And then how many do you need? So the obvious bound is, and this is important, you can select the same set multiple times. Right? You have to be allowed that, because otherwise you may not even have an f-fold covering. But how many sets do you need to select, counting your sets with multiplicity? And so the obvious bound is simply f times the covering number, right? I mean, if I can use 10 sets to cover my whole set, and then if I want to cover everything 5 times, then 50 sets will be enough, because, well, I just select each of the 10 sets 5 times, and I'm done. Well, the Lovász-Stein lemma says that essentially this tau star times the log of the max size of a set is a bound for tau. So we should have like f times this. But instead, it turns out, so what we noticed with Sasha Polyansky is that if you modify your greedy algorithm and do a little bit of different type of greedy algorithm, so it's still a greedy algorithm, but with different costs or different weights, then you achieve that as long as this f is not too large, the same bound, essentially the same bound up to this constant factor, will hold. So in other words, let's say you are in d-dimensional, So you want to cover, let's say you want to cover 100 times. Essentially, what it says is that you still don't need. You definitely don't need 100 times the number that you would get from the Lovász-Stein lemma. You need essentially as many. You need the same number as what the Lovász-Stein lemma gives. So there are two interpretations of this result. One is that, well, as I said, this is an obvious estimate. Covering f times is at most. You don't need more than, well, covering once f times. And so this beats that. Of course, you can't really beat it when f is too large. I mean, if f is really large, then you can't do better than that. But another interpretation is that if you have an f-fold covering, then it's not hard to see that this tau f over f, this quantity tends to the fractional covering number, right? Because if I cover everything 1,000 times, I could just say that all the selected sets get weight 1 over 1,000, and then I get a fractional covering. So this is clear, and this lemma somehow quantifies the speed of this convergence. So it kind of tells you that you don't have to go further than log of the max size there to essentially reach this this limit, or to be very close to this limit. So going back to geometry, let's say you want to cover space. Let's say you want to cover d-dimensional space not once but 5 times. The lemma says that, well, essentially the same bound, essentially the same as Rogers. This is Rogers bound. This d log d bound will be fine. If you want to cover it 10 times, you still don't need many more. And the reason it comes so easily is because we separated the combinatorial and geometric part. So now I still have 2 minutes left, 3 minutes left, so let me move on to different types of questions. So one is covering by homothets. So now the question is, instead of trying to cover space by homothets of a given convex body, now we have, so instead of translates, now we have homothets. Okay, so we have this lambda 1k, lambda 2k, etc. So shrunk or magnified copies of k. And the question is, are there translation vectors such that this family with those translations will cover space? And well, an obvious necessary condition for them to cover space is that the total volume has to be infinite, right? So that's a condition. But then the question is it sufficient? And if so, then how well can you cover space? So how well can you choose your translation vectors? What's the density that you can reach? And well, an obvious thing is if these lambdas are essentially equal, if they have a limit point which is not 0, then of course it's essentially a translative covering problem, and then you can give a covering of the whole space with the same density that you could achieve with using just translates of k. So this theta of k is the translative covering density. So this is obvious. So the interesting part is when this lambda is bounded, so we don't have too large lambdas, and the only limit point it has is 0. So in this case, it turns out that you can actually cover space with density 1, which is not counterintuitive. It says that, well, these you have bigger and smaller and smaller and smaller copies, then with the right translations you can cover all of space, essentially everything being covered only once. Now, on the other hand, going in the opposite direction, if lambda is unbounded, then well, we managed to prove this bound, not even about density, but slightly more precisely about maximum multiplicity, that no point will be covered more than 40 times. So this is a joint result with Nora Frankel and Naszódi that we achieved recently. And the idea is it needs some geometric ideas, and for the proof of this you need Vitalis covering theorem. Yes, one more slide, and yeah, maybe I will just skip this because there's going to be a good talk about covering the sphere by strips. So I just want to say again, happy birthday, and I hope that 20 years from now we're going to have the same conference for the same 3 people.